Hello everybody, welcome back to the Graph Algorithms course. Today we're going to talk about previsit and postvisit orderings. And these are sort of some numbers that you can do when running a depth-first search that sort of records some information about the order in which you visited vertices. And we're going to discuss a little bit about why these numbers might be important, but mostly it's going to be that they will turn out to be very useful in some algorithms we're going to discuss later. Okay, so let's talk about depth-first search, which is an algorithm that we came up with last time. And it's a little bit weird as an algorithm. Because, well, what happens when you run depth-first search? It doesn't return anything. It does modify the state of some things. It marks vertices as visited or unvisited. But in the end, it just ends up marking every vertex as being visited. If all that you wanted to do was mark every vertex as visited, there are easier ways to do it. On the other hand, like the order in which we sort of find these vertices in sort of a way that involves their connectivity is actually very useful. For example, with slight modifications, keeping track of a little bit of data, we saw how to use depth-first search to compute connected components. So in general, if we want to make depth-first search useful, we need to keep track of some extra information about its execution. So what we're going to do for this is we're going to augment some of its functions in order to store additional information. So for example, let's look at Explore. What we're going to do is we're going to mark the vertex v as visited. But then before we do anything else, we're going to run some previsit function. This is just some extra things that we're doing to sort of maybe record some information or do a little bit of extra work, sort of just as we found this new vertex. Then we go through this loop over neighbors and exploring all the unexplored neighbors. And then right before we're about to finish exploring V, we run some other post-visit blocks, some thing that we do it right before we're finishing up. Okay, so what are these functions going to be? They could be a number of things. We'll come up with an example shortly. But the idea is to augment our functions a little bit to keep track of some extra information. So what sort of extra information do we want? Well, one thing we might want to do is to keep track of sort of what order we visit vertices in. And so one way to do this is we sort of have a clock. This clock keeps track of time. It ticks forward once every time we hit a previsit or a post-visit for a vertex. Every time we discover a new vertex for the first time or sort of leave an old vertex for the last time. And every time we do one of these things, we'll also record the time at which that happens. So for each vertex v, we'll have a record of the previsit time and the post-visit time. So to see what I mean by this, let's look again at this example. The clock starts at 1. We visit our first vertex. It gets its previsit number assigned as 1. From there, we explore the second vertex, which is previsit 2, and then the third vertex, which gets previsit of 3. From there, we start. Well, we're done exploring that vertex. All of its neighbors have already been visited. So we assign it post-visit 4 and move on. This other vertex gets post-visit 5. We now have a new vertex to explore. It gets previsit 6 and post-visit 7. And our original guy gets post-visit 8. And that wraps up our first explore. We now find a new vertex who gets previsit 9 and his neighbor previsit 10. And then they get post-visit numbers 11 and 12. Finally, we've got a new guy with previsit 13, and his neighbors get 14 and 15, and then they get post-visit 16, 17, and 18 as we wrap them up, and we're now done. We've just assigned the numbers 1 through 18 as the previsit and post-visit numbers of these 9 different vertices. So the way we compute these is actually pretty easy. We just have to initialize our clock to be 1 at the beginning of our depth-first search. And then in the previsit block of our explore, we set the previsit number of v to be this clock value and increment the clock. And for the post-visit block, we set the post-visit number of the vertex to be the clock value and increment the clock. Very easy, doesn't really change the runtime of anything, but allows us to compute these numbers. Now, what are these useful for? Well, really the previsit and post-visit numbers, they tell us something about the execution of the depth-first search. And we'll see a little bit of this as we prove the following lemma. So suppose that you have any two vertices u and v. From these you get intervals pre of u to post of u, and then pre of v to post of v. These are two intervals, and the claim is that these intervals are either nested or disjoint. And in particular, whether they are nested or disjoint will actually tell us something useful about the sort of way in which the DepthFirst search ran on these two vertices. So let's take a look at what we mean by this. If you have two intervals, there are a few ways in which they could intersect with each other. Firstly, it could be the case that one interval is strictly contained in the other one. This means that they're nested. It could also be that they're disjoint from each other, that they don't overlap at all. Finally, we could have two intervals that are interleaved. They sort of overlap over part of their ends, but not over the entire interval of either side. And what we're saying in this lemma is that the interleaved case is actually not possible. Okay, so let's see the proof. We first assume that without loss of generality, the first visit to U happens before the first visit to V. We now have two cases to consider. Firstly, it could be that we find V for the first time in the midst of exploring U. And this sort of means that in the DepthFirst search tree that we produced by this exploration, we found V as a descendant of U. We sort of found V while exploring U. The second thing is we could find V after we're done exploring U. So sort of V and U are on different branches of the tree. They're cousins of each other. Okay, so let's look at the first case. If we explore V while we're in the middle of exploring U, then explore V is actually being run as a subroutine of explore U. And because of the way subroutines work, we can't finish exploring U until we're finished exploring V. And therefore the post of U is bigger than the post of V, and these two intervals are nested. In the second case, we explore V after we're done exploring U. So we start exploring U, and then we finish exploring U. And then sometime later, we start exploring V and then finish exploring V. And so these intervals are going to be disjoint. And so these are the only cases. The intervals are nested or they're disjoint. And which case we're in will actually tell us something useful about the order in which we visited vertices in this graph. Now, just to review, we've got these two tables here of sort of pre and post numbers, but only one of them is a possibly valid table of pre and post numbers. Which one is not valid? Well, the one on the right can't be correct because these two intervals from pre to post for vertices A and B are interleaved, and that can't happen. Okay, so that's sort of pre and post orders. We'll see a lot more usefulness later, but in the next lecture, we're going to introduce something a little bit more new. We've been talking a lot about undirected graphs. Here we're going to be talking about what happens when the edges actually have an orientation to them. So please come back next time and we can talk about that.